这讲的是你们修正过的。徽号是邮件。
我 approve 了，你们能进来吗？我要给 host 还是？
So our topic is very free, so you can interrupt the speaker anytime you want. Okay. Any question? Okay. Okay. Let me stay here. So our second speaker is also from IBS, Dr. Zhong. He is going to talk about the compact Kähler threefold with the action of an abelian group action of maximal dynamical rank. Okay, let me start. Thank you.
Thank you very much for the introduction. So today I would like to discuss some dynamics on the automorphism groups of compact Kähler threefolds. So I'm going to discuss the 5 parts. The first is I would like to recall the dynamical degree and the entropy, which are essential notions in the dynamical systems. And the second, I would like to introduce some background and previous results on this project. And then, since I would like to consider the non-projective Kähler setting, so I would like to first review the some essential results in the projective setting, and then compare with our analytic case. And after that, I would like to introduce my main result and some sketch proofs. And finally, I will ask some open questions. So now we start from a compact Kähler manifold of dimension n with a Kähler form omega. And we denote by this auto X as the group of all holomorphic automorphisms of X. And we define the piece dynamical degree. We use this dPg to denote this piece dynamical degree. We define it as the maximum of the modulus of this eigenvalue of this pullback G on the P-piece cohomology space. We note that for every endomorphism G, its pullback induce a linear map on this vector space HPP. Okay, so in other words, the piece dynamical degree is the spectral radius of this induced map. Okay, so we can also calculate this dPg as the limit of this integrations. Okay. So for every P, order P, we can define this piece dynamical degree. Then we denote this HAG to be the algebraic entropy of this G. Okay, so we denote this, we let this HAG to be the maximum of the logarithm of the piece dynamical degree when this P runs from 0 to n. So actually, there is another notion called the topological entropy. We use this HTG. I will not discuss this HTG today, but a very deep result by Gromov and Yongding, they together show that the algebraic entropy coincides with the topological entropy. So the topological entropy is a dynamical invariant measuring the divergence of the orbits. So today we will mainly focus on the our algebraic entropy. So note that there is a very interesting property of the dynamical degree. This is proved by Nowatzki and Kaiser. Okay, so this said the dynamical degree owns the concavity. Okay, so this means there exist 2 integers u and v, such that from d0g to dug the dynamical degree increase, and then from dug to dvg all of them coincide, and finally from dvg to dng the dynamical degree decrease. So we say that this G is of positive entropy if the topological entropy is positive. or equivalently, the first dynamical degree is greater than or greater than 1. So this is an element. So usually we can also discuss the subgroup of the automorphism group. So we say a subgroup G is of positive entropy if every non-trivial element in G is of positive entropy. Okay, so this notion, to the best knowledge of myself, it was first introduced by Ding and Sibony in 2004. Okay, so also we can discuss the dynamical degree in the singular setting. Okay, so we start from a projective variety X or a compact Kähler space, and we define the first dynamical degree to be the spectral radius of the pullback G on the nylon-Savary space or the border-chain cohomology space for a non-projective variety. Okay, and we say that this G is of positive entropy if the first dynamical degree is greater than 1, or otherwise we say it is of 0 entropy or non-entropy. And by a deep result of Ding and Sibony, the dynamical degrees can also be defined for dominant meromorphic maps, and they are by meromorphic invariance. Okay, so this is the dynamical degrees and entropy I would like to review. Okay, now let's enter into the second part of my talk. So let me introduce some background and the previous results in this, on this project. Okay. So motivated by Smiles' work, Ding and Sibony studied the structure for an abelian subgroup of automorphism group X. So here we require this subgroup to be abelian. So this theorem says that we can give a very explicit structure for the abelian subgroup of the automorphism group of a compact Kähler manifold. Okay, so here we denote by this G to be the abelian subgroup of an automorphism group X. Okay. Then the subset U of the elements of 0 entropy is a subgroup. And after we quotient this U, so there is a free abelian subgroup H, which is of positive entropy, and it has rank no more than n-1. Here, this n is the dimension of the manifold. Okay, such that this G is isomorphic to the product of U and H. So in other words, after you quotient this H, the 0 entropy part, the remaining positive entropy part is a free abelian group of rank no more than n-1, no more than dimension x minus 1. And in particular, if the rank H, the rank of the positive entropy part achieves the maximal rank. In other words, the rank H is equal to dimension x minus 1, then the group U is a finite group. This U is the non-entropy part. Okay, note also that the third item in this theorem is optimal. So in other words, for every n, there is an n-dimensional complex torus T such that the automorphism group of this complex torus T contains a free abelian group Z n-1 of positive entropy. So this said that in Ding and Sibony's theorem, the third item is optimal. Okay, so later on, generalize the abelian group case. Zhong can show the solvable group case. Actually, he proved a theorem of T's type for compact Kähler manifolds. So meanwhile, the Ding-Sibony's rank estimates were thus extended. Okay, so this theorem is essentially proved by Zhong and later on formulated in the joint paper by Campana, Wang, and Zhong. So we let this G be a subgroup where this X is a compact Kähler manifold of dimension n. And then there are two situations. Either this G contains a free non-abelian subgroup Z star Z, okay, or there is a finite index solvable subgroup H such that the subset N of zero entropy elements of H is normal in H. Okay, so actually the logic is, so this auto X is a automorphism group, and for every G, there is no requirements on this G. So either this G contains a non-abelian free group Z star Z, or there exists another subgroup H of finite index. Okay, finite index. Such that if we discuss this H, and then we take all of the zero entropy elements N in this H, then this N is normal in H, and the quotient is the positive entropy part, and the rank, the H over N, is a free abelian group of rank no more than a -1. Okay. So in particular, this automorphism group X satisfies the T's alternative. Okay. So the T's theorem says that every linear group G over R satisfies the T's alternative. In other words, any subgroup of G either has a free non-abelian subgroup or is virtually solvable. Okay. So virtually solvable means it possesses a finite index solvable subgroup. So in our case, this H, okay, after replace this G by a finite index subgroup H, then this H is virtually solvable. Okay. So Zhong generalized this T's theorem to the automorphism group of compact Kähler manifolds. And actually, this T's alternative for auto X was first conjectured in the joint work by Kohn, Oguiso, and Zhong in 2009. And later on, Hu extends the Zhong's T's alternative to positive characteristics. Okay, okay, so based on this theorem, the following is our main question. So can we classify the n-dimensional compact Kähler manifolds admitting a free abelian group of automorphisms of rank R with this R no more than a -1, which is of positive entropy? Because we, according to Dean Sibony and Zhong's their theorems, the positive entropy part, the rank, is no more than a -1. Okay. So in particular, can we classify the extremal case when this rank R achieves the maximum? So let's see some lower dimensional case. So on the curve case, it is trivial because every automorphism of curves is definitely zero entropy. Okay. So the first interesting example is on surface. Okay. So by content in 1999, if X is a smooth complex compact surface, no matter Kähler or not, okay. If it admits an automorphism of positive entropy, then such X can never have many choices. Okay, there are only 4 choices. So either X is a complex torus, or an Eric surface, or a K3 surface, or a non-minimal rational surface.
So in most of the cases are Kähler, so only accept the non-minimal rational surface.
Yeah. Okay. Then the next theorem classifies the projective case with maximal dynamical rank. Okay, so here I use the dynamical rank to represent the rank of the positive entropy part. Okay, so in our case, the dynamical rank is no more than a -1. Okay, so we start from a normal projective variety of dimension n admitting the action of the group G of positive entropy. And then there are 2 cases. So if X is not rationally connected, then with this G replaced by a finite index subgroup, such X is birational to a quotient of a complex torus. And we can also, Zhong can also show the the birational map from this initial X to the quotient of complex torus is G equivalent. So there are two cases when this dynamical rank achieves the maximum. So either this X is rationally connected or this X is covered by complex torus. So actually, Zhong also treated the case when G is virtually solvable. Okay, but for the convenience of our talk, I only deal with the abelian group case. So there is a more complete version of the above theorem in Zhong's paper, where some conditions can be further weakened. So the next example tells us that the rational case can happen. Okay, so there exists a rational threefold X with at worst KLT singularities, such that this X is a quasi-tau quotient of a three-dimensional abelian variety. And also, such X admits an abelian subgroup G of maximal rank, because here this n is equal to 3, so the maximal rank is equal to 2. Okay, so this G is Z direct sum with Z, okay, which is of positive entropy and of maximal dynamical rank. So here, so we can see in the, here in the last theorem, so Oguiso's example says that there exists a threefold X which is rational, and also this X is covered by complex torus. So another interesting example is, can we find a rational variety X or rationally connected variety X such that it admits the positive entropy action group G, okay, and but it is not bimeromorphic to a quotient of a complex torus, because you can see Oguiso's example is the intersection of the two situations. So we would like to know whether there are some examples such that these two conditions are mutually exclusive. Okay, so now let me recall the G equivalency. Okay, so a rational or a meromorphic map from X to Y. Here, this G means the pair G means the action group. Okay, on X of projective varieties or compact Kähler spaces. We say this rational map or meromorphic map is G equivalent if this action group G descends to a biregular action on Y. So with this G equivalency kept in mind, there is a deep theorem by Hironaka on the equivalent resolution. Okay, so for any analytic space defined over C, there is a canonical desingularization X tilde such that this map is this resolution map is G equivalent. Okay. The automorphism auto X invariant. Okay. The existence of resolutions of singularities of analytic space in characteristic 0 was confirmed by Hironaka. And the proof has been simplified by Billstone and Melman and Villamel in their series of works. And recently, it seems it has also many breakthroughs in the positive characteristics. Okay. But here we focus on the characteristic 0. Okay, another property about the G equivalent fibration. Okay, so this is initially proposed by Zhong and later on explicitly formulated by Hu. Okay, so if we start from Xg, a pair where this G is a free abelian group of positive entropy, and if there is a G equivalent surjective morphism pi from X to Y of projective varieties or compact Kähler spaces with the dimension X greater than dimension Y of positive, or both of them are positive dimension, then the dynamical rank of this G on X is no more than the dynamical rank of this G on Y plus dimension X minus dimension Y minus 1. Here, this dynamical rank is defined as the rank of the positive entropy part. Because by the structural theorem, there exists the non-entropy part. And after you modulo this non-entropy part, it is a free abelian group, and the rank is no more than dimension x minus 1. Okay, so here that gives an estimate on the dynamical rank. So in the following, let me have a brief review of Zhong's program. Okay. So first, if X is uniruled, then this automorphism G of automorphism group G descends to the biregular action G on Y by Nakayama's special maximal rationally connected fibration. Then we apply the above property to this G equivalent resolution. We can show such X is rationally connected. Okay, so recall that in Zhong's program, there are only two cases. Either X is rationally connected or X is bimeromorphic to a quotient of a complex torus. So here, if X is uniruled, then we can show such X is rationally connected under our dynamical assumption. So in the following, we will only focus on the non-uniruled case. Okay, so if X is not uniruled, then by the famous paper of Boxen, Demai, Pong, and Peter Nell in 2013, they show that the canonical divisor is pseudo-effective. Okay, and then in this case, we can run the G equivalent minimal model program with scaling. So the second case is our main focus today. Okay, because by using the balanced analytic cycle theory, we can also show the first item in our analytic case. So in other words, if we have a uniruled Kähler threefolds, and we also assume there is a free abelian group of maximal rank of positive entropy on this uniruled threefold, then by the Brunella's paper, we can also show such X is rationally connected. And in particular, it is projective. So our main focus is on the case when the canonical divisor is pseudo-effective. Okay. So the problem is how to make sure the G equivalency. So here we need a very important divisor class. Okay. So this is proved by Ding and Siboni in the abelian group case, and later on generalized by Zhong to the solvable group case. Okay. So if we start from a normal projective variety or a compact Kähler manifold of dimension n, and we assume there is a group G of rank R, which is free abelian of positive entropy with this rank R no more than -1. Then there are NF R Cartier divisors, or correspondingly NF 1-1 classes L1 to LR plus 1, such that, note that all of these Li are NF, okay? Such that each Li is a common eigenvector of G. So the common eigenvector means there are R plus 1 characters chi from G to R, such that the pullback of this Li is equal to chi G Li for any G. Okay, and the second property is the intersection product from L1 to LR plus 1 is non-zero as an element in the R plus 1 cohomology. Okay, so you can see in particular, if you take this R to be our maximal rank case, which is R is equal to n-1, then you will find n NF eigenvectors L1 to Ln such that the intersection product L1 to Ln is non-zero. In particular, it is positive because all of them are NF, so their intersection should be non-negative. So by our second property, it should be positive. In other words, the sum is a big divisor. So in particular, if R is equal to n-1 being maximum, then we get a NF and a big R Cartier R divisor A, which is the sum of this Li. Okay. And also by the property of this A, by our choice of this A, if you repeatedly use the projection formula, then you can show for every G periodic KK class alpha, this A power n minus K times alpha is equal to 0. So you can see in particular, if you take this alpha to be the first chain class or the second chain class, then you will get the vanishing, okay, by the property of this A. Okay, so keep this second property in mind. We will use this later on. Okay, now using such A, we continue to recall Zhang's program for the pure case. Okay, so in the following, let us prove the G equivariancy. Okay. So by the Zhong theorem, we know there are only finitely many Kx plus A negative extreme arrays. So we may assume all of such Kx plus A negative extreme arrays are all A trivial. So you can see this is simply from the Zhong theorem, because you know when you running the minimal model program, so by using the Zhong theorem, so if this A is 0, then this is the sum of the positive K positive non-negative part and the countably many rational curves generated by this extreme arrays. And however, if you add a smaller ample divisor A or nef and big divisor A, then such sum is finitely many. So by using this property repeatedly, we can show our implications. So every Kx plus A negative extreme arrays are all A trivial if you replace this A by a multiple. And then by the projection formula, the G image of this Kx plus A negative extreme array is still Kx plus A negative. So we get the G equivariancy. So finally, this A, since this A is the contraction is A trivial, so this A is the pullback of a nef R Cartier R divisor from downstairs by the Zhong theorem. So all of the property of this A can descend to downstairs. And then by BCHM in 2010, such G equivalent MMP with scaling will terminate in finitely many steps. So we get the end product Y with this KY plus AY being nef. So we may start from beginning that we may assume this KY plus AY is nef and B. And then by the base point free theorem, we get a birational morphism from Y to Z such that this nef and big divisor K plus A is the pullback of an ample divisor AZ plus KZ plus AZ. And then by using the sigma decomposition for this KZ, Zhang can show that this KZ is indeed Q trivial, and hence AZ is ample. And finally, by using our useful property of this A, the second chain class is also equal to 0 by the pseudo-effectivity of by Milka's pseudo-effectivity of the second chain class. So finally, this Z is the Q abelian variety. Okay, so this is the first chain class vanishing, the second chain class vanishing. Then this X is covered by this Z is covered by abelian varieties. Okay, so this is proved by Yao in the smooth case, and in the singular case, Grab and Quebec and Peter Nail, they generalize to the case normal projective variety, which is smooth in codimension 2. Okay, and finally, it was extended by Lu and Taji to the KLT singularities. So this is a very useful criteria to see whether the variety is covered by complex torus. Okay, so now let me introduce my main result and the proofs. Okay, so we start from a Q factorial compact Kähler KLT threefold pair. And we assume there is an action of a free abelian group G, which is Z2 being maximal rank. Okay, because in our case, we deal with the threefold case, okay, of positive entropy and of maximal rank. And we also assume every irreducible component of the support of the boundary is G periodic. Okay, so this assumption is for the convenience to run the G equivalent minimal model program. So if there is a pair XDG satisfying the hypothesis, and if X is not rationally connected, then with this G replaced by a finite index subgroup, we have the following three properties. So first, there is a G equivalent bimeromorphic map from X to Z, such that this Z is covered by a complex torus, which is tau in codimension 1. Okay, so this is the notion of quasi-tau. So in the singular case, by the purity of branch locals, we know if this is, so the quasi-tau means this map, this morphism from T to Z, from the complex torus to this Z is tau in codimension 1. Okay. And the second, this Z is isomorphic to T over H, and this H is a finite group acting freely outside a finite set of a complex 3 torus. And actually, this H is the Galois group of this T over Z. And moreover, the quotient morphism from T to Z is also G equivalent. And the last property is there is no positive dimensional G periodic proper subvarieties of Z. Okay, so this is due to the property of this Z itself. Okay, so in particular, the meromorphic map X from X to Z in the first item is indeed holomorphic. So note that the last property of the bimeromorphic map from X to Z is holomorphic is only true in dimension 3. Okay, in high dimensional case, the flipping contraction may be more complex, so we cannot easily deduce from the first property of the item 3. But in dimension 3, it is okay. Okay, so this is our main theorem. So note that the rationally connected compact Kähler manifolds are projective. So we immediately have the following corollary. So if we deal with the non-algebraic compact Kähler threefold admitting an action of a free abelian group G of positive entropy, then this X is bimeromorphic to the quotient of a complex 3 torus, with the quotient morphism being tau outside finitely many points. Okay, so for this proof, we need to use the G. We need to establish the G equivalent minimal model program for non-projective Kähler threefolds. Okay, so this without any dynamics, the theory for the minimal model program on Kähler threefolds are established very recently. Okay, so we use this recent result to show our theory. But before that, we need to do some preparations. So first, applying the Ding and Siboni's paper to the pullback of our NAP cone to the G equivalent resolution x tilde to x, we can get 3 G common NAP eigenvectors, Xc1, Xc2, and Xc3, such that the sum is a NAP and B class. Because by the construction, the intersection product of this Xc1, Xc2, and Xc3 is positive. So their sum is NAP and B. And the question is, similar to the projective setting, we would like to know whether there are only finitely many Kx plus Kc negative or non-positive extreme arrays in the NA bar X. Here, this NA bar X is generated, is a closure of the cone generated by n-1 positive closed currents. Okay, And we would like to also to know whether they are generated by rational curves. In the projective setting, it is easy because we have the Kohn theorem and we can easily deduce such result. But in the Kähler setting, this is highly non-trivial, especially in the fibration case, in the non-pseudo-effective KX canonical divisor case. Okay. So let me give a brief review on the minimal model program for Kähler varieties. Okay. So Fujino established the minimal model program for Q factorial log surface in the Fujiki class last year. And Philip and Tossati proved the base point free theorem in dimension 2 on the Kähler surface. Okay. Here, all of things we don't assume any projectivity in such manifolds or varieties. Okay. And in dimension 3 case, Hurin and Peter Nail established the minimal model program for Q factorial terminal Kähler threefolds. And later on, Campana, Hurin, and Peter Nail, they proved the abundance for compact Kähler terminal threefolds, except that this X is a simple threefold of Cordero dimension 0. And generalized to the log pair case, Des and O proved the log abundance for compact Kähler log canonical threefold pair with this K plus delta being nef, and the numerical dimension is not equal to 2. Okay, so the numerical dimension is defined to be the highest degree such that the self-intersection is non-zero, but this degree plus 1, the intersection will be 0. So in other words, here, for example, if this numerical dimension is 2, this means kx plus delta square is non-zero, but kx plus delta cubic is 0. Okay. So they have some in this numerical dimension equal to 0, equal to 2, they have some difficulties to show the abundance or the log abundance. Okay. And based on this abundance theorem, Campana, Hurin, and Peter Nail, and Des O, Des Haken, in this series of papers, they finally established the existence of the minimal model program for DLT pairs on Kähler threefolds. And finally, Des and Haken, as an application, Des and Haken proved the base point free theorem on Kähler threefolds on the DLT pairs. So this is a very big difference compared with the projective setting, because in the projective setting, usually we use the base point free theorem to establish the minimal model program. However, in the Kähler setting, the base point free theorem is just an application of the minimal model program. So they first established the minimal model program, and then they proved the base point free theorem. So the direction is somehow conversely. Okay. Okay, so now let me introduce the very important proposition on the finiteness of K plus Kc negative extreme race. So here, this Kc, recall that this Kc is the sum of nef eigenvectors. So this Kc is a nef and a big class. Okay. So let X be a normal Q factorial compact Kähler threefold, and the delta is an effective Q divisor, such that this X delta has only KLT singularities. And we let this alpha be a nef and a big class on X. And suppose that one of the following holds. So either this Kx plus delta is pseudo-effective, or Kx plus delta is not pseudo-effective, but Kx plus delta plus alpha is a big class. Then we can show there are only finitely many K plus delta plus alpha negative extreme race, and all of them are generated by rational curves. So you can compare this theorem, this proposition with our projective setting. So you can see in our projective setting, we simply take here this our A is also nef and big. So that alpha is our A here. So in the projective setting, this is easily deduced from the Kohn theorem. So we don't mind whether K plus delta is pseudo-effective or not, okay? Just follows from the Kohn theorem. However, in the Kähler setting, we don't have this full version of the Kohn theorem. So for the pseudo-effective case, I guess there is a full version of the Kohn theorem, but especially in the second case, we don't have the Kohn theorem. Okay, so our proofs relies on the Kohn theorem. And under the above condition, we can show there is a fixed number D such that every K plus delta negative extreme rate R is generated by a curve L with the intersection with minus K minus D, minus delta is no more than D. Okay. And note that the Kohn theorem is okay for the non-uniruled threefold case, but there are some differences with the projected case when X is uniruled. So especially when K plus delta is not pseudo-effective, the base point freeze, the Kohn theorem has not been established yet. So we need to assume some technical condition. For example, K plus delta plus alpha is a big class. Okay, but this is enough for us in our situation. Okay, then let's see the end product of the G equivalent K plus Kc minimal model program. Okay, so finally we should get the NF divisor K plus Kc. Okay, so note that here we run the K plus Kc minimal model program, and this Kc may not be integral. So this is not the same as the projective setting, because in the projective setting, you can always make this A to be the rational boundary, and then you can adjust this A to make it to be a KLT pair. But in here, we just simply run this K plus Kc minimal model program for this Kc being just a NF and big one class. So if this K plus Kc is NF, then there is a G equivalent by meromorphic map such that this Y is covered by complex torus. Okay, so similar as the projective setting, with this Kc replaced by a multiple, we may assume K plus Kc is also NF and big for every K and every K plus Kc trivial ray R is also Kc trivial. Okay, so this technique is due to the proposition I just introduced. Okay, and then by the base point free theorem, there is a holomorphic map from X to Y with connected fibers such that our K plus Kc is a pullback of beta. Okay, so note that this beta is a Kähler class now. Okay, by the base point free theorem. And then you can see from the projection formula, this beta is also the sum of the canonical divisor and another class, Kcy. Okay. So note that this Tor is G equivalent, but the proof is very troublesome when compared with the projective case. So we skip the technical proof here. And we can also similarly show this Tor is Kc trivial. And hence, by the Kohn theorem, this Kc is the pullback of the another NF and B class Kcy from downstairs. Okay, because Kc has zero intersection with every contracted ray. So by the contraction theorem, such Kc is a pullback of Kcy from downstairs. And then you can see this beta is the sum of canonical divisor and the Kcy. Okay. So then we would like to show this Ky is trivial. Okay, so if this Ky is trivial, then this Kcy itself is a Kähler class. And then since this Kcy is G periodic, we will have the zero intersection with the second Chern class. Then we can apply the Yale's generalized theorem on the Kähler setting, Kähler threefolds. In other words, the first Chern class vanishing, the second Chern class vanishing, at least on threefold case, it is covered by complex torus. Then we are done. Okay, so there is another technical lemma which says that the non-locals of this Kcy coincides with the union of G periodic proper analytic subvarieties. Okay, so this non-locals is defined as the union of positive dimensional proper analytic subvariety V, such that this Xy restriction on V is not big. So this means you can see, because in our case, Xy is nav. Okay, so this Xy restriction on V not big. So this is equivalent to the self-intersection of Xy on V, dimension V. This is equal to 0. Okay, so this is equivalent to Xy power dimension V times V. Okay, this is 0. So this is the definition for the non-bigness of Xy restriction on V. Here, we need the naveness of Xy. Okay. So, this lemma says that the non-locals of this Xy is equal to the union of G periodic proper analytic subvariety. So this means that if you have such V, such that this Xy restriction on V is not big, then such V is G periodic. Okay, recall that this G is our free abelian group Z, Z2, which is of positive entropy. Okay, so this lemma says this V is G periodic. And then there are some technical steps for us to show this Xy is indeed Kähler. Okay, so we can take a G equivalent resolution with the non-Kähler locals, such that the non-Kähler locals coincides with the non-locals. Okay, so the non-locals means you take all of such V with such that this restriction is not big. Okay, and the non-Kähler locals means the complement of the maximum Kähler locals. Okay. So this is proved by Collins and Tosatti in 2015. And then by Damawi and Boxham's paper, we may choose a Kähler current T with analytic singularities precisely along the non-Kähler locals. Okay. Then after blowing up the ideal sheaf and taking Hironaka's resolution, in other words, with this Y1 further replaced by this Y2, we can show the pullback of this Xy is the sum of a Kähler class omega and an exceptional divisor E. Okay, this E is an effective R divisor, and such that the support of the image of E on this Y1 coincides with the non-Kähler locals. And then by the Hodge index theorem, this Xy restriction on V is equal, we can show it is numerical trivial for every positive dimensional G periodic proper subvarieties. Note that this is not the same as the intersection, top intersection equal to 0. Here, what I said, this Xy restriction on V numerical trivial, this means this Xy has 0 intersection with every curve on V. Okay, so this is much stronger than this property. So this is proved by the Hodge index theorem. And so finally, we can show the pullback of this Xy on this effective divisor E is 0. And then furthermore, by the Hodge-Riemann theorem, we can show the pullback of Ky times this omega square is also equal to 0. So in particular, we can show this Ky is numerical trivial. Okay, note that this Ky is pseudo-effective. So Ky is numerical trivial, and the K plus Xy is also Kähler. Then finally, we can show Xy is a Kähler class. And then after we show this Xy is Kähler class, then it has 0 intersection with C2y. So by the we can also by the pseudo effectivity of this the second Chen class, okay, then we can show this C2y is also equal to 0. Here, this C2y is defined by Graf and Kirchner in 2020 in the non-projective setting. Okay, so this is, we call it the orbifold second Chen class. And then finally, this Y is the complex 3 torus by the characterization of Graf and Kirchner. Then the proposition is proved. So some remarks. So the G equivalency of the quotient morphism from T to Y shares almost the same proof as in the projective setting. So there is this is not very interesting since Zhong has already showed the G equivalency, so we omit the proof. And also about another remark on the characterization of the Q complex torus. So the Graf and Kähler characterization of Q complex 3 torus has been recently extended to arbitrary dimension. Okay, assuming the smoothness in codimension 2. Okay, this joint work is by Claudon, Graf, and Gunesia last year. So the next step should be further generalize this to the KLT singularities in the analytic setting. Okay. And they also showed the semi-positivity of the second Chern class for a general compact Kähler space with the second Chern class vanishing, which is KLT and smooth in codimension 2. Okay, so the smooth in codimension 2 is important in their joint paper. So let me summarize our proofs. So we start from the initial X and run the K plus Kasi minimal model program G equivalently. And then we achieve this Xn. Okay, so we end up with this Xn such that Kxn plus Kasi Xn is NF. And then such Xn admits a G equivalent by holomorphic map to Y. Here, this Y is covered by complex torus. Okay. So this is all the proofs. So there are two important steps. First, we run the G equivalent minimal model program to Xn, end up with the NF and canonical divisor. Okay, Kxn plus Kcxn. Okay, and then we use the base point free theorem to show and also show the G equivalency. So finally, I would like to ask some open questions. So in the view of Ding Sibony and Zhang's works, we would like to know the general case when G is assumed to be a free abelian group with lower rank. So you can see the first question is, if X is a compact Kähler manifold or a projective variety of dimension n, and if this free abelian group of positive entropy is of rank R no more than n-1, can we classify such X? You know, when R is equal to n-1, it has been intensively studied by Zhong, but we would like to know whether, what about the other situations? For example, R is equal to n-2, or R is equal to 1, something like this, okay? So the most difficult part is, in this case, we cannot have the nice Kasi, okay? Because we will not have enough eigenvectors. NF eigenvectors, so we may not get a NF and big divisor Kasi. Okay, because previously, if R is equal to n-1, then we can get a sum of n NF eigenvectors, and hence we can get a NF and B class. But here in the lower rank case, such Kasi may not exist. Okay, so Hu and Li, they partially gives a try in the rank when G is equal to, the rank G is n-2, which we call the sub-maximal rank. Okay, so they just did a try. But even in the rank n-2, they haven't given a complete answer to this question. Okay, so only some partial results are obtained. So we would like to know whether about the next case. So also in the view of the Oguiso's example on the rational KLT threefold being a quotient of an abelian variety, we finally ask the following question. In other words, I just mentioned in the middle of our talk, so whether there is a variety X such that it is rationally connected, but it is not bimeromorphic to the quasi-tau quotient of a complex torus. Okay, so here this means the two situations in our case, rationally connected or the quotient of complex torus, whether they are mutually exclusive. Okay, we don't know whether this is true. So because we know they may have some intersections, because Oguiso's examples told us there exists the torus of a complex, the quotient of a complex torus which is rationally connected. but we don't know whether there exists such an example. Okay, so I think I will stop here.
Any question?
Oh,
okay, so I have a question. So you have asked your question too. Let me first mention my question too. So is it known for surface, for example, like a abelian surface quotient by some finite group? Is it known to have some maximal rank automorphism?
I think in the surface case, if you have positive entropy, the rank can only be 1, cannot have more than rank 2. So I mean, if in this case, you have a positive entropy automorphism, then by consensus results, it's either K3 surface, Henrich surface, non-minimum rational, or Henrich's non-minimal or complex torus. Yeah. So in this case, I think there is.
X is a quotient of E cross E. Surface E cross E, then quotient by finite group, then you get a rational surface. I guess then it is very easy.
But this is not the quasi-tau quotient, right? You may have some. You may have some ramification along the.
I don't. If the quotient of the group is good, it's hard to say.
Yeah.
Another question is since you work for the Kähler threefold, but you highly rely on the minimum program. So if the minimum model program holds for the high dimensional Kähler manifold, can you also prove this? Generalize your result to the arbitrary dimensional case?
Yeah, I think there are 2 gaps in the high dimensional case. The first is the minimum model program. And another thing is even you know the minimum model program, the base point Fourier theorem is not very easy to deduce.
So this is still the issue of the minimum.
Yeah. This is still, I believe if the base point Fourier theorem is fine for in any dimensional, then we from the last step of the minimum model program, we can get the quotient of complex torus. Yeah.
Okay, so since you mentioned the generalization from the projective case to the Kähler manifold case,
yeah.
So is it trivial? Maybe is it trivial for the Murchison manifold? Because you mentioned about the minimal program.
Yeah. Thanks. But if this is you mean Murchison but not Kähler?
Murchison Kähler is projective, right?
Yeah. Because so if you assume Murchison, then you may not assume the Kähler.
Yeah. But Murchison can be reduced to projective.
Yeah. So if you take the G equivalent resolution, then we just.
But in general, we don't.
But there is no G equivalent resolution to.
This is not known. Yeah.
I see.
Yeah. This is a conjecture, I guess.
So then we need to first have the equivalent resolution to its smooth model.
Yeah.
To its project. The G equivalent blow up to make it projective.
If your automorphism group is connected, then everything is fine. But I guess here your automorphism group is in general not connected.
Yeah, it may not be connected. Yeah. So, but here can we just do the auto zero equivalent?
Yes, we can, but we cannot get any information on G. We don't know any information.
I see. Because G itself is discrete.
Your group, your G action on the cohomology group is not trivial in general.
Yeah, not trivial. Yeah.
Any other question? If no, let's thank the speakers again.
Okay, thank you very much.
Thank you very much for the. Okay, so we stop here. Okay, thank you very much for attending.
Thank you for coming. So maybe we stop the.
You can stop the show.
Okay, so maybe we stop the meeting. Okay, thanks. See you.
So where is your talk from?
to
3 p.m.
Yeah, but it's a colloquial light. So
okay.
it's gonna be very